Okay, what I'm going to do now is just show some basic variations. And I'm going to do this a little bit differently. Instead of trying to do everything live one-handed, what I'm going to do is substitute in some various loads in this position and some various Zeners in this position, and turning the circuit on and off. And while I'm doing that, I will put the video camera on a stand and then just point it at the oscilloscope screen so that you can see what's going on. And I'll be just narrating and telling you what the different loads are that I'm putting in there. Okay, so first of all, before we get started, let me make sure that the bass lines haven't drifted. The scope should be nice and warm now. And let's see. Okay, so the top trace, channel B, is currently being displayed at 0.1 volts per division, 100 millivolts per division, and we are not, let's see, we're using the Velleman probe, and it's set at the not attenuated, the 1x position. Okay, so we'll be reading true on the B. And this is the trace across the current viewing resistor, the B probe. Okay, and it's a 1 ohm resistor, so 100 millivolts will be 100 milliamps on that, assuming no correction for inductive reactance. This is the battery trace down here, the A trace, and it's going to be shown at 20 volts per division. And that's where its zero baseline is, and there's its probe monitoring the circuit right there. Okay, so what I'm going to do then is, well, first let's get the scope back on and get it triggering. Alright. Okay, so what I'll be doing then is I'll be subbing in some different components here for the load. I've got this socket arranged so that it's actually, I can put two components in series in that socket. But right now I have just the one LED in there. This is the anode end and this is the cathode end, and they're marked on that little piece of masking tape there. And then this is where the Zener goes in the circuit. I've put a socket in there. This is the current viewing resistor end, and then this is the other diode junction here where the Zener normally goes. And then the cathode band is in that direction, so the cathode would be on this side of the Zener. Okay. So I'm going to just sub in some components there, and I'll tell you what I'm doing while looking at this. While you're looking at the screen. Okay, so I'm just going to trigger back. Okay, so right now all that's in there is the one LED and no Zener diode. Okay. Oh, the time base. Sorry, the time base right now is 0.2 of a microsecond per division. So 0.2 of a microsecond per division, and the other thing that I can do is look up here at the Phillips counter, and all I have to do is just take the probe out of the battery lead and plug it into the Phillips counter, or the battery channel. Plug it into the Phillips counter right there, and then the counter gives me an estimate of the frequency, and right now it's saying 7 megahertz, which can't be right. Can it be right? About 3.5 megahertz right now, and let's just check that by doing the computation on the screen here. We're at 0.2 per division, 0.2 of a microsecond, so we've got 1, 2, 3, 4, 5, and 5.7. Let's say we got 5.7 traces. Sorry, 5.7. 5.7 divided by 0.0234. 5.6 equals 356, 3.56 megahertz. So yeah, okay, so that's a correct frequency right now. We're showing about 3.5 megahertz on there. Okay, And let me get the battery signal back on there. There you go. Okay. All right. Now it's my. I believe this is going to give a fairly strong negative power product because you have a battery peak that goes below 0 plus this big peak here too. Okay. So now what I'm going to do is I'm going to take out. No, what I'm going to do now is put in. Sorry. I'm going to put in the 5.1 volt Zener in the Zener hole. Okay. Like that. Okay. So that's with the 5.1 volt Zener in there, and as you can see, the amplitude of some of the peaks has grown and the frequency of the oscillation has gone way down. And let me just get an idea of what that frequency is on the Philips counter. And the Philips says 1.56 megahertz for that. Okay, so I believe that. Alright, so that's with the 1 LED for the load and the 5.1 Zener in there. That's a beautiful little set of waveforms, don't you think? I do. I love the look of a nice inductive ring down. Okay, so now I'm going to take the 5.1 Zener out and go back up to that frequency. Okay. Now what I'm going to do is take a capacitor. No, first I'll just take a piece of wire, just a short, and I'll just short where that Zener goes with a piece of wire. Okay. This is a direct short here, like that, and then to reestablish the trigger. See there? So now you can see that we have no current indicated up there, and we're at the straight battery voltage right there. And when I remove the short, the circuit comes back on and oscillates. Okay. So now what I'm going to do is take a little capacitor, a 0.01 capacitor, and do the same thing with it. Put it where the Zener was. Point there. And now I get this weird waveform at a lower frequency up there on the top. And when I remove it, it comes back to normal. Okay. So now I'm going to remove the LED load and I'm going to replace it with just an inductor. This is just a 2.2 microhenry inductor where the LED was. Okay. Right there. Right there. Okay, so that's no LED, that's just a 2.2 microhenry inductor in there, and no Zener diode. And let's get a reading of the frequency on that. With the Philips. Let's see here. What does the Philips say? Sorry, the Philips is having difficulties with this particular signal. Okay, there we go. It's 3.1 megahertz again. All right. And there's our battery trace again. Okay, now I'm going to do the same thing with the capacitor. Right now we're looking at an inductive load of 2.2 microhenries. And now I'm going to touch the 0.1 microfarad capacitor across where the Zener goes. And there's that weird change. And now when I remove the capacitor, it comes back to normal. Okay, now what I'm going to do is change the load to a 2.2 microhenry inductor and a 100 ohm resistor in series. Okay. Alright, that's the 2.2 microhenry inductor and the 1 ohm resistor in series. Now I'm going to take the capacitor and short it across where the Zener goes right now. Okay. Notice where the current is up there. And now I removed the capacitor and there's nothing there now. the circuit didn't start oscillating again, and the current stayed at this level right here, which is about 40 millivolts, which translates into 40 microamps, or milliamps of current right there. Now when I turn the circuit off, you can see that current drop down to 0. When I turn it back on, the oscillations come back. If I can get them to trigger, there we are. Okay, let me do that again. I'm going to take a capacitor and put it across that load, and as soon as I do, then the oscillations go away, but I've got that residual current. The MOSFET is just staying on. Okay, so I have to turn the circuit off and then turn it back on to get those oscillations back. And I'm going to crank up the volts per division. So now we're going to be looking at this one at 50 millivolts per division, or 50 milliamps, because of the 1 ohm current resistor. Okay, so once again, if I just take a piece of wire and short where the Zener goes, like that, the oscillations disappear, but there is no current. Now when I remove the wire, the oscillations come back immediately. Okay, but if I use a capacitor and I short where the Zener goes, you see what happened? The current the oscillations died, but the current jumped up to 40 milliamps. And now when I remove the capacitor, nothing happens. The oscillations don't come back. The current stays up there. I have to turn the unit off and then turn it back on to reestablish the oscillations. Looks like that battery voltage may have drifted a little. Let me reset it. Okay, there. Okay, but look, this is going to be a really strong negative power product, I think. Alright, and that's with the load being a 100 ohm resistor and a 2.2 microhenry inductor in series, and that's me just touching the load there. Okay, so, oh yeah, with the Zener, 5.1 volt Zener, stick it in there, and and with this load, with the inductive load with the resistor, not much happens when I put the Zener, the 5.1 volt Zener in. There's a little change in the waveform, but not really anything significant happens. If I turn the Zener around the wrong way where it's conducting, there's the standard thing that happens with the short across where the Zener goes. It's just like a piece of wire somewhere. Like that. Okay, so now I'm going to go back to the single LED load there, and that gives us really strong oscillations on that, so I'm going to turn that down to, again, to 0.1 volt per division, which translates to 100 milliamps per division on that. And that's with no Zener right now. And okay, variations. Thank you for watching.